All right, welcome back everybody. Here we go for part 2 of the 9-2 notes. Now we're going to not be multiplying as much as simplifying, and we're going to have some division involved. As usual, this will be a little bit more challenging than the front side with multiplication. First, let's revisit rationalizing the denominator. Again, we don't want fractions inside of our square roots, and we also don't want to have any square roots in denominators of fractions. We're going to make sure we take care of that. The square root of 2 over 3, we can rewrite that as the square root of 2 over the square root of 3. What we do is always multiply by whatever the denominator is. I say always. There are actually going to be times when we're going to be clever about what we choose to multiply by. Right now, if we just multiply by radical 3, radical 2 times radical 3 gets us radical 6. Radical 3 times radical 3 is radical 9, and the square root of 9 is 3. So now our denominator is a rational number, and so we're happy. Yay! Yay! All right, we're moving on to the next one. So again, I'm separating these two into two different radicals, radical 5x over radical 7z. I'm going to multiply the top and the bottom by radical 7z. When we do that, I'm actually not writing out what it equals to, but it would be the square root of 49z squared, and the square root of 49z squared would be 7z, and our denominator would be rationalized. 5 times 7 is 35. Now, I always have to be aware. It's like, ooh, is there a perfect square hiding inside of there? But it's only 5 times 7 that are the factors of 35. So no, this is going to remain radical 35. Number 19, I'm going to intentionally not do something just to show you what can happen. 2/6 could actually be reduced, and later we're going to do this in subsequent problems to do that first, and that's actually a wise thing. But here I'm going to show you what happens. You can still get to the answer if you don't do that. I'm just going to follow the tried and true, just going to multiply by the denominator, which is 6y inside the radical. When I multiply that, 2 times 6 is 12, x squared times y is x squared y, and now this is 6y. However, the 12 here has a perfect square inside of it. It's up there, right by the mouse. Radical 4 times radical 3. So this is going to become 2 radical 3. So the 2 is here, the 3 is inside the radical. X squared is a perfect square, so the square root of x squared is x, and this comes outside. All right, now we're looking at this, and we think, gosh, aren't I done yet, Mr. Rooks? And it's like, no, not quite, because 2 over 6 is a fraction that can be reduced. So 2/6 becomes 1/3, so the 2 is gone. There's a little 1 there that you can't really see, and there we have 3y down at the bottom. All right, same thing can apply if we've got a different index here. In this case, I've got an index of 4, so we're talking about a fourth root. All right, so here we go. Now, I'm not looking for perfect squares anymore. I'm looking to have a perfect power of 4. So what I'm going to multiply by, this 3, is I'm going to multiply by 3 cubed, because I need basically 3 to the 4th power. 3 times 3 times 3 times 3. I have 1 3. I need 3 more. So 3 to the 3rd, when I multiply 3 to the 3rd times 3, would get me 3 to the 4th. And the 4th root of 3 to the 4th would be 3. Same thing with y. I need it to be a multiple of 4. The smallest multiple of 4 is 4. If I multiply this by y to the 3rd, this will become y to the 4th. And the 4th root of y to the 4th is y. All right, up top here, 3 to the 3rd is actually 27, and 27 times 2 is 54. X to the 2nd is inside, and a y to the 3rd inside. Might want to go check in your calculator to see if there are any perfect powers of 4 that are factors of 54. Mercifully, you will find that there is not. This is less than 4, so it cannot be simplified anymore. And that also is less than 4, so it as well cannot be simplified anymore. Stick a fork in it, we're done. Alright, now what's advantageous to us is, if possible, we can go ahead and simplify our radicals. Basically, in reverse to having this separated, we're going to think of it as being this over this inside, and just merely simplify the fractions first. So 24 over 6, 24 divides evenly by 6, and that's 4. X to the 5th over x cubed. Again, now you have to go with how you simplify when you have division with exponents. Some of you have been taught to just subtract. 5 minus 3 is 2. Some of you do the whole canceling thing where you picture this as x times x times x times x times x. This is x times x times x. The x's go to war with each other. When they're done fighting it out, you're going to have 2 x's left over, and they're going to be on the top. So the entire denominator is gone. It's basically over 1, but of course we don't write things over 1. This is perfect squares galore, so the square root of 4 is 2, and the square root of x squared is x. So our final answer here, simplified, is 2x. Example 22. So now we're going to look at where the somewhat larger things are in the denominator here. So when we simplify 3/24, we're going to get 1 over 8. X squared over x cubed, if you're doing the subtraction method, it's 2 minus 3 is negative 1. But x to the negative first power is 1 over x. So the x ends up in the denominator. If you're doing the canceling method, this is x times x, this is x times x times x. By the time the war is over, there's going to be 1 x left over, and it is going to be in the denominator. Alright, once we have that, it is time to do the rationalization step. So we have radical 8x. Now I could multiply by radical 8x. If I do that, I'm going to end up with an 8 inside of here, and that's going to have to be simplified, and that's going to be a pain in our backside. So this is where we can save ourselves a little trouble by being clever, because that's what we're in. We're in the clever business here. So we got to think, what is a perfect square that I could get out of 8 by multiplying? And that would be 16. 8 times 2 is 16. So if I multiply by 2 instead of 8, I won't have further simplifying to do. Separate paper, you might want to go ahead and try doing radical 8x on top and bottom, and you'll see you'll end up in the same place, but this is a little bit more efficient. So this is going to be radical 16x squared, and the square root of that is 4x. On top here, 1 times 2x is 2x, and we're done. Alright, example 23. 10 over 60. Again, you can use math fraction if you're not good at simplifying fractions. Go to 10 over 60 and go math fraction on your calculator, and it will tell you that that is 1 over 6. X over x squared simplifies to 1 over x. So again, I have radical 6x in the denominator. This case, I can't think of anything other than there's no perfect squares inside of 6 here to worry about, so I can just go ahead and multiply by radical 6x. Radical 6x times radical 6x is radical 36x squared, and that's 6x. You got to avoid the temptation to think that you can now simplify this. Again, things in radicals are like protected. You cannot simplify them with things below that are not in radicals. So avoid that temptation to mark through those 6's and those x's and think that the whole thing just somehow becomes the square root of 1. Example 24. 2 over 8 is 1/4. The x in the x squared becomes 1 over x. Y to the 8th over y squared, again, that would be 8 minus 2 is 6, and that would go on top. 4 is a perfect square. I really don't have to multiply by anything to get that to be a perfect square. You're perfect just the way you are. X, I need to multiply it by x to get it to be x squared. So I'm just going to multiply radical x and radical x on the top and the bottom. Of course, we're really just multiplying by 1. That's what makes this legal, because all of this, radical x over radical x, that's just 1. Alright, so the cube root of y to the 6th is y to the 3rd. This you cannot take the square root of. This is the square root of 4x squared when you multiply it, and that is 2x. Our denominator does not have any square roots in it. Nothing inside that radical can be simplified, so happy days. We're moving on to the next problem. Alright, number 25 here. So now we've got an index of 3. We're taking third roots, cube roots. 16 over 2 is 8. X to the 4th minus the little hidden 1 is x to the 3rd. These are both perfect. Cube root of 8 is 2. Cube root of x to the 3rd is x. Very nice. Starts out easy, gets a little harder. Simplifying 2 over 100, that is 1 over 50. X to the 4th over x to the 11th simplifies to x to the 7th. Again, if you're doing a subtraction method, 4 minus 11 is negative 7. Negative exponents drop down into the denominator and become positive there. It is x to the 7th. Alright, now it gets a little tricky. You've got to go looking at your list of perfect cubes. Somehow we want 50. You've got to multiply it by something to get it to be a perfect power of 3. If you look at your list, hopefully you'll look at your calculator and y equals x cubed and find, ooh, there's 1,000. And since this ends in 0 and 1,000 ends in 0, you know that 1,000 ought to divide by 50. So it does, and it's 20. 50 times 20 is actually the number that we're looking for. Okay, so now we're doing third roots. The key with third roots is we want this to be a multiple of 3. So I have to ask myself, what is the next multiple of 3 that's larger than 7? Well, the next one would be 9. So I've got to multiply x to the 7th times something to get it to be x to the 9th, which would be x squared, again because you're adding the radicals. Okay, when we do this, 1 times this is just the cube root of 20x squared. Here we get the cube root of 1,000x to the 9th. Cube root of 1,000 is 10. Again, to find our exponent here, we're going to take our exponent and divide it by the index. That results in x to the 3rd power. Alright, we're doing some serious work now. This is good. Keep with it. Take a little break anytime you need to. Feel free to hit pause here. I'm just going to roll on through and wrap this up here. Alright, 8 over 8. Woohoo, that's just 1. X to the 12th over x to the 3rd is x to the 9th. Cube root of x to the 9th is x to the 3rd. That was not a very inspired problem on my part, but you know, every now and then you got to do things that are kind of easy. Makes life a little simpler. Oh no, trouble ahead here. Negative exponents. Dun 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 dun. Negative exponents, you know, I've taught this before. I say it's the story of these sad little exponents. They're never happy where they are. These exponents up here that are negative, the negative 4, they're so sad and miserable. If you move them down there, they become positive. This negative 3, they're also not happy. They move up to the top, and now they're happy where they are. Now we can do our great big canceling step. 24 over 6 is 4. X to the 3rd, x to the 4th, cancel each other out. And you're left with x in the denominator. Alright, then we just multiply by radical x over radical x. 4 is a perfect square there, as it turns out, so we can take the square root of that. That's 2 radical x over x. Example 29. 12 over 3 is 4. It's nice, perfect square. Now, these negative 9, that moves down to the bottom. It really becomes 1 over x to the 9th. So you've got 1 over x to the 9th, and x to the 3rd's already there, so that becomes x to the 12th in the denominator. So I can simplify 12 over 3 to get this 4. X to the 12th mercifully is a perfect square, so I really don't have to rationalize it because I can just take the square root of it. It's x to the 6th power. Alright, as they say in Hawaii, it's the big kahuna now, the grand finale. I hope you're excited. Here it comes, the last problem, the uber challenging x's and y's and negatives and everything all thrown into one problem. Let's do it! X to the negative 5th, that's negative. It's going to move down there and join its little x to the 6 buddies down there and have a big party together of x's down there. That's going to be x to the 11th in the denominator. Alright, I'm going to kind of do this all at once here. There are two ways to do it. One is to move them first, and this is going to become 2 on the top and 8 on the bottom. And so then, after you have y times y over y to the 8th, after the simplifying happens, you'll end up with y to the 6th in the denominator. If you like the subtraction method, then you're going to do negative 8 minus negative 2. That becomes negative 8 plus 2, which is negative 6. That moves down to the bottom, and y to the 6th is in the denominator. Okay. X to the 11th. Again, we're dealing with an index of 2. I need this to become a multiple of 2. So instead of multiplying by x to the 11th and end up with simplifying to do, the very next multiple of 2 is 12. So I can just multiply by x, and this will become x to the 12th. Y to the 6th, I don't have to do anything with that because it's already an even number, and so it is a perfect square. All I have to do is multiply by radical x over radical x. I get radical x over this. The square root of x to the 12th is x to the 6th, and the square root of y to the 6th is y to the 3rd. Yay! We're all done. Now it's time to go do some homework and some classwork. Again, if you don't have... Hey, we're all excited. Let's go do it. Oh, somebody's so excited they fell over. So, if you don't have a printer, of course, you're going to have to go old school on this and just get out some old-fashioned notebook paper, write down the problems that are available on Canvas, and knock yourselves out. I have no idea how all of this is going to end up being graded or what the whole process is for grades that's coming ahead, but we're just going to rumble through all this the best we can, and we'll see you when I see you. Hopefully it'll be April, well, whenever the deadline next date is. I'll see you guys soon. Thanks for your attention and for watching my video. Bye.